This video is for the 5th day of the extra topics with Physics AP, and amongst other things we're going to take a look at matter waves and X-ray crystallography, and I think we're on this page right here. And for this first little topic off the start, we're going to take a look at how not only can you get diffraction happening with light, in this case it's going to be X-rays, but you can also get diffraction happening with matter if you think about the matter as being waves. This time, instead of having slits inside a mask like we did near the beginning of the course, we're going to talk about how you can actually use a crystal, the actual atom sites, the lattice sites as we call them, as your source for the individual little waves that come off and then undergo constructive and destructive interference. So let's actually start right in the middle of the page here, and we'll take a look at what is going on in some sort of chemistry crystal. And so we're accustomed to seeing these openings in a mask with diffraction happening from them. And now what's actually going to happen is these lattice sites are actually going to be kind of the locations where the waves are going to come off. And then there's going to be some really cool diffraction pattern that shows up on some sort of detector. It could be some photographic film or some sort of electronic detector later. Now, we're accustomed to seeing this with light. And the idea there is we could send in some light of different colors, different wavelengths, but we're going to be way up high, like even perhaps past ultraviolet. We might go even through X-rays, where we can look at those, just more energetic light, and then we might keep on going into talking about gamma rays. And so when we look at that spectrum there, as you move from ultraviolet light through X-rays towards gamma rays, the energy is increasing. So this is more energy as you go in that direction for those three that are listed. Wavelength, of course, is the other way around because energy goes with frequency. So UV has a bigger wavelength than X-rays. X-rays have bigger wavelengths than gamma rays. And that wavelength is important when we go to look at these wave effects. So we're going to talk about X-rays here. Maybe typically we might be talking about a wavelength of, just going to pick a number here, let's say around 1 nanometer. And let's go and take a look and see exactly what would happen when you're working with 1 nanometer. If we're trying to get to the point where we can talk about the amount of energy that's involved in that story, we could go and do V is equal to lambda F, and that way we can figure out what the frequency is. So if we're talking about light, okay, UV, X-rays, and gamma rays, that's all light. So 3 times 10 to the 8 is your velocity. The wavelength, 1 nanometer, 1 times 10 to the negative 9. And then let's go look for the frequency. And when you do that, you find the frequency for this particular radiation would be around 3 times 10 to the 17 hertz. So it's oscillating a little faster than just visible light would be. Now, talking to Max Planck, saying, okay, photons, if you've got that for the frequency, then how much energy are we going to have there? If you run an E equals HF calculation, you find out that the energy involved to do that is 2 times 10 to the negative 16 joules. So if you send in some light with that much energy per photon, that would have the right wavelength. And if, here comes kind of the big thing here, if your lattice sites happen to be 1 nanometer apart, then you could actually get some really interesting effects, right? If the lattice site spacing is, around that wavelength spacing. But sometimes for some crystals, the lattice sites are much tighter than that. They're closer than that. And we have to actually use something that has an even smaller wavelength in order to get it to work. And what you can do is you can fire electrons at your crystal lattice. So if you have electrons being launched, so this is going to be like an electron gun that's going to be used to launch some electrons, right? So that's all this device here is, just using our idea of parallel plates. Okay, we've done that several times. Let's make some numbers up. Let's say your electron gun is using 800 volts for the accelerating voltage. And we're going to then take that electron and fire it at a crystal lattice. And it turns out you get patterns because that electron is not actually a dot. It's actually made up of waves. And so if you wanted to run through the numbers on this, then the first thing I would do is say, okay, how much energy is that electron going to get? We can just do a QV calculation. So we're looking at charge of an electron, 1.6, 10 to the negative 19 coulombs, and then 800 joules per coulomb for our 800 volts. And those electrons that you're launching at your lattice, they have an energy of 1.28 times 10 to the negative 16 joules. Okay, that's great. Well, we're heading to the point where we're going to go and figure out that de Broglie matter wavelength. So the first thing we have to do now is make a little stop through physics 11 with kinetic energy. So I'm just going to do EK is equal to 1/2 mv squared. I'm going to run some numbers here using the electron. So I'd be putting the electron's mass in and saying, hey, electron, you've got 1.28 times 10 to the negative 16 joules. So how fast are you going? It turns out that electron would be going 1.68 times 10 to the 7 meters per second. So not quite relativistic speeds. All right, great. Well, now here comes the interesting part. Let's go and take a look at matter wavelengths. When you're talking about wavelengths of particles that are moving at high speeds, this is the equation that you use for matter waves. And when you actually try that out, you find that this electron, which we would classically think of as being like a dot, no, it's actually this wave and has some wavelength to it. And it ends up being, in this case, around 4.33 times 10 to the negative 11 meters. Okay, kind of awkward to write like that. But if you write it in nanometers, that ends up being 0.043 nanometers. Pretty tiny. You know, maybe we should be talking about picometers at this point. Well, I want to leave it as nanometers just so that you can compare over to when we were talking about X-rays. So X-rays might have a wavelength of around a nanometer. But if you want to be working with some sort of crystal structure and you're going to be bouncing waves off of it, and you want to look for the diffraction patterns, if you desire to have a smaller wavelength, then one option would be to fire electrons at it with that speed. And at that speed, they would have these wavelengths at 0.043 nanometers. So depending on the crystal size, it might be more appropriate to use electrons or it might be more appropriate to use X-rays. But now you've got those options. And it turns out it does work. When you fire electrons at these crystals of that size, you do get these patterns. So another piece of evidence that quantum mechanics is right, that matter is actually really all about waves. Next little topic here, it's going to be a quick little topic. I'm going to talk about quantum mechanical wave functions. It is a part of Physics AP's curriculum. What's interesting is you probably really won't do this in earnest until at least third year physics, maybe even fourth year. So this is absolutely a tip of the iceberg, just a little bit of foreshadowing for some of the stuff that you're going to do when you're playing around with this in quantum mechanics at university. And these pictures here, I've got pictures of this this wave, and it's the Greek letter psi that we're actually using here. It kind of looks like a crazy little pitchfork sitting upside down. And it's actually the symbol we use to represent the wave function. And that picture there could be the story of an electron inside a box where it can't leave the box. And those gray borders are the edges of the box. And what's really interesting is at this level of physics, that picture, that is the electron. And you might go, oh, it's representing the electron? No, that is an electron in a box. So you no longer say, oh yeah, the electron's like a little dot, a little particle, and it can go and sit in a box. You would actually say, no, 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 the whole thing is nothing but this picture, and the little dot is just some metaphor for how you're looking at it. But this is actually everything. And I'm actually going to write exactly that down. That wave function, psi, which depends on where you're located, okay, you can see it kind of goes up and down and up and down. That is everything in the world of quantum mechanics. Everything you need to worry about can be calculated once you know what's going on with that wave function. It is actually going to reveal every possible observable thing you can imagine about this electron. I want to just tell you a couple of quick little points, 3 quick little points about this wave function thing. It is actually a complex number, so it's got an imaginary part as well as a real part. But first key thing, some takeaways for Physics AP. One of them is that these peaks in the graph, okay, these peaks in amplitude, so peaks on the graph, You can see that these graphs have different peaks to them. Peaks on the graph are more probable places to find the particle. That is a key thing. That is worthy of a box. You never know exactly where you would go and say, oh, I have found the particle. Right? It could actually be located in lots of different places, and you have to go and look for it, and then it will show up in one of them. And the places where the peaks are the places where the probability is actually the best at finding that particle. Now, if you're looking at it going, what's this n equals 1, 2, 3, 4? That electron might have different energy levels when it's sitting inside the box. And that n equals 1 graph is the wave function for a very low energy electron sitting in the box. And you can see that it's more probable that you'll find it near the center. And then as you start to have this thing go to various different higher energy levels, then you start to see these places where it's not probable to find it, but then other places where it is. N equals 2 is more energetic than n equals 1, and n equals 3 more energetic than n equals 2. And it continues to go that way. A couple last little thoughts. This is just foreshadowing for stuff you'll see in third year. You can actually find all of the kind of the area, if you wish, underneath that wave function. If you go and integrate that wave function, you have to do some sort of fancy stuff where you actually kind of look at the size of the wave function. So you do some weird absolute value thing for complex numbers. But if you integrate that from one side of space to the other, that always equals 1. That's how we actually set up our quantum mechanics. So you might be going, well, wait a minute, how do you show more energy then? I would have thought the graph would have been higher if there's more energy. And the answer is no. You don't try to actually make the graph taller to have more energy. You actually end up adding more bumps. So more bumps in the graph in this particular story here would actually mean a higher energy level. All right, that idea of wave functions actually leads to the whole idea of that complex pattern of chemistry orbitals, which you probably talked about in chemistry 11. And so what we saw in chemistry 11 was that, this idea of, oh yeah, there's the nucleus and then the electrons, the little dots, they're flying around that nucleus. That's overly simplified. It's technically wrong. It doesn't look like that, right? That's not the way that things actually go. Instead, you have to start filling up the various orbitals to figure out what this atom's going to look like. So for example, let's say you were to take sulfur. Okay, so atomic number 16, mass typically of 32. It's got 16 protons. It's going to have 16 electrons that need to be positioned inside that atom, well, outside the atom, orbiting around it. And the way that you figure out where they're located, where it's going to go, is you start filling up these little chemistry orbital energy tables. And each place can actually have 2 electrons in it, because electrons have, according to quantum mechanics, this option of being what we call spin up or spin down. And so you start filling from the bottom up. So the first electron might go here, and a little upward arrow means, oh yeah, let's go spin up. The second electron we go to place can go in the same location, but it has to go spin down. You can have 2 spin ups in the same place, and you can't put another electron there. It's something called the Pauli exclusion principle. It says, no, each state for electrons can only be occupied once. Now it's a different state if it's spin up and then spin down, so you can sneak an up and down in that same place. Well, that's 2. Then you have to go to this next orbital up. And we're going to talk about what that means by the next orbital here in a second. And then you can go spin down. Now I've got to 4. I can put a few here at this energy level. So 2 P's are more energetic than 2 S's. And that's interesting because we didn't talk about that for the hydrogen atom. Then you go to the 3S. You can put a couple in there. And we'll keep working our way up. So how many have we got so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then you could go like 13, 14, 15, and 16. So we're going to probably end up with this partially filled orbital there, that 3p orbital, right? It could actually take 6, but we're only going to put 4 in there. And that's why In chemistry, you might have said, oh yeah, the arrangement, the electron arrangement is 1s2, so 2 of them in that 1s orbital, and then 2s2, 2p6, 3s2, and then this next one, for the 3p's, we're only going to put 4 in there, even though there was room for more. And so what's going on with all these orbitals, and why does it not look like what it did for the hydrogen atom, where you just had the 1, and then the 2, and then the 3? Why is it splitting? Why are there multiple options for where the 3's go? And the answer is because there's 16 electrons, and they start to interact with each other. And as they do, these various little orbital locations start to spread and split. And then you end up with situations where the 3D is actually higher energy than the 4s. And it's really this electron-electron interaction that's happening there. Now, these pictures, which you may have seen in Chemistry 11, these are the orbital shapes, right, for the places where you might go and find where that electron is. These are based on quantum mechanics, where you actually go and look at those wave functions. The wave functions extend past those pictures. So one key thing to realize is that these are kind of the 90% regions, the 90% orbital regions. And so if you were to go and imagine the wave function in this three-dimensional space wrapping around that atom, then it's not just like this picture back here, this kind of like, one-dimensional picture sideways. It's this 3D thing, and those bumps will show you where it's likely for you to find it. But they do extend off to the side. They continue to go out for an orbital picture for an atom, but it's pretty unlikely to find it out there. And so these drawings, some of them are really bizarre looking. These drawings actually show you where you would expect to find the electron 90% of the time. So you're most likely to find it right there. Okay, last thing, kind of dealing with this idea of mass and energy and waves and how quantum mechanics all ties in. Let's actually go and take a look at the equivalence of mass and energy here. This is a story we could have done in Physics 11, a story about radioactive decay. We've got some plutonium, and it's going to just naturally undergo transmutation, and it's going to form uranium-235, and just looking at the numbers, we'd have a 4 and a 2, that would be helium, an alpha particle. Now, it turns out, if you're really careful and check where all the electrons are, this thing is positively charged. It doesn't have any electrons, didn't take any with it. And that means that this uranium still has the 94 electrons, so it's actually got a charge of -2. It's not neutral. Okay, I just want to show you that there's another option for trying to figure out how much energy is going to be given off when this radioactive event happens. What we would have done in Physics 11 is we would have said, okay, this thing here, that's going to undergo the radioactive decay. If you're really, really careful with your measurements, you'll see that it's got a little bit more mass than the right-hand side. So this side over here doesn't have as much mass as the left side. It's a very, very small change. And the Chemistry 11 kind of topic or curriculum would say, no, mass is conserved. Well, mass and energy are conserved, and we're going to convert a little bit of that mass into energy. Over on the left side of the page, I'm going to do it the way that we would have if we were playing this game in Physics 11. We would be working with these atomic mass unit values kind of up in the top, these U values. And we would have done this. You probably have to write pretty small to sneak this all in. But looking at the end of the story, I'm going to look up this uranium here. So I just find the uranium. There it is, 235, 043, 924. So I want to take that, 235, 043, 924, and add on the helium. I do see some helium there. Technically, both of these numbers are wrong. They're wrong because of that charge issue, but they're wrong in the opposite directions by the same amount. So this works fine. If you add that up, it looks like the after part of the story has a mass of 239.046,526. And those are atomic mass units. In a simplified sense, you can think of them as being like 239 times the mass of a proton. Okay, it's roughly speaking like that. Okay, so that's what mass you've got at the end of the day. Now, we're going to lose a little mass here from that purple side to that green side. So I want to go and figure out, well, how much mass is actually going to get lost in this process, what we call the mass defect. So I'm going to take that 239.0522157 for the plutonium, just looking that up in the table, and then subtracting off what I see for the mass on the after side, 239.046.526. You know, you technically probably should be going final minus initial, and you're going to get a negative to see that it's a drop in mass. I get it. But I just want to see it as a positive. It doesn't really matter. So that change in mass, that missing mass from one side to the other, we're seeing a loss of decimal 0.005631 atomic mass units. Okay, where again, these are roughly speaking the mass of a proton. So about half of 1% the mass of a proton. That's what that's saying. It's gone. It's been converted into energy. Now, remember this value, this atomic mass unit, the mass roughly speaking of a proton is actually 1.66 times 10 to the negative 27 kilograms. So if I go and switch that mass over into kilograms, which is what we needed to do when we were playing this game in Physics 11. If I switch it over, I can rewrite this story of missing mass as being, oh yeah, we have lost 9.35 times 10 to the negative 30 kilograms every single time one of these transmutation events happen. Now finally, once you're in kilograms, we can go and do E equals mc squared, because E equals mc squared demands that we work in kilograms. So how much energy do we get when that small amount of mass, only a small portion of the mass disappears? So I take that missing mass, I'm going to put it in here, multiply by the speed of light squared, and I end up with 8.4, around 8.41 times 10 to the negative 13 joules. Okay, now a different way to do this. There's just another option here for how you talk about how much mass each one of these particles is. You can actually talk about them as being, whatever you prefer, mega electron volts or giga electron volts divided by c squared. It's just a totally different option for how you can talk about it. So if I was to use that set of numbers, I'm now going to be focusing on looking on this bottom row. So I'm going to use, for the uranium and the helium, I'm going to use this number here, and I'm going to use this number here for the helium, and I'm going to use plutonium. When I'm ready for it, I'll be grabbing that number. Okay, so to do this, I would say, well, at the end of the story, the masses are 218.9434 plus 3.7284. Just in this very interesting method of measuring the mass, okay, in energy divided by c squared units. And it looks like afterwards, that right-hand side has a mass of 222.6718. Again, unusual units, okay? These giga electron volts, that's energy, divided by c squared. All right, now I'm going to go and find the missing mass. See, some people just find this a more convenient way of actually working, and you'll see why here in a second. Subtracting, I could go 222.6771. That's the plutonium, right from the table, minus this number we just figured out, 222.6718. And what I find is there's some missing mass. The missing mass is decimal 0053 in these rather unusual units. Energy divided by c squared. Well, this is now where it's really, really, really nice. Because when you go to figure out how much is that just in terms of energy, the whole idea is that you're supposed to go E is equal to mc squared. You're supposed to take the mass that's missing and then multiply by the speed of light squared. So you have to do this awkward multiplication where you multiply by 3 times 10 to the 8 and then square it. But now it's actually really easy, and it's because this c squared is the way I'm going to talk about the speed of light. And we've been talking about c squared right here for that speed of light being squared. And so now when I actually multiply by c squared, all that happens are the units change. And it's so convenient to do this. Now we can just say, all right, the amount of energy involved in that story is going to be 0.0053. And it'll be just nothing but giga electron volts. So this is very, very common. You're going to see this, especially at university, where you don't always use joules. You don't always use the units that you're accustomed to. You don't always use 3 times 10 to the 8 meters per second squared. Sometimes it's just nicer to say C, right? And so here you can rearrange this if you want. If you're looking at it going, I'd rather just talk about that in terms of something a little more convenient. It can maybe move that 3 spots. This is 5.3 mega electron volts. And if you really, really do want to convert that back to joules, you can. And when I tried that out, I had basically the same answer as before. There's just some round off errors here. That's the only reason why it's wrong, is I actually only have a couple sig figs here looking at that 0053. So I'm not disturbed at all that this is a slightly different number. It's just purely a round off thing. So you'll often talk about the mass of particles in these interesting energy divided by speed of light units. So for an electron, yeah, you can say it's 9.11 10 to the negative 31 kilograms. Or you can say, as you see up here in the table, that this is the actual mass, right, for an electron, right? Just an energy divided by the speed of light squared. And so you'll see that kind of notation happening all the time. Now that kind of finishes up our work with that kind of modern physics stuff. And now we're going to transition over a little bit. And the second part of this, if you want to call it a chapter, just of extra topics that we haven't quite touched on yet, is actually going to be about electricity and magnetism. And so we're going to go and just take a look at some different ways to look at some stuff that you've already seen. So this is totally transitioning now to, I guess, what we would have done in our 5th unit of Physics 12. I want to begin by taking a look at the equation for force that you have when you were looking back at electrostatics. We said, force was equal to K Q all over R squared. And then we actually even said, if you want to, you can go and find electric field. You could do K Q all over R squared. And so field, that kind of warns you about how positive things get pushed, right? So a note here warns us about forces. I'm going to say on protons. The key thing is positive charges that could get dropped into the story. And so we drew pictures just like these two when we were talking about what happens when you look at the field around a positive charge or a negative charge. And if you were to drop a little proton on scene right here, well, it's going to get shoved away. And that's what that picture there is trying to show. But now, in addition to showing those electric field lines, right, that's what's there in blue, right? I can see those there. Yep, there's the E field lines, the little warning about that. We can also, on the same picture, drop in some voltage lines. So we saw in that chapter that voltage was kind of a warning about energy, right? It was K, Q all over just an R. So voltage is just a warning, kind of a pre-calculation about energy. Well, it needed to know how far you were going to be away from that point charge. And the farther you got away, the lower the voltage would be until you were infinitely far away, and then the voltage would actually be 0. Now, I'm going to draw some pictures. I'm going to cheat and draw them this way. I'm going to draw some pictures of some circles that are going to get just superimposed right on top of this picture here. Maybe make it a little tinier. This circle is nice because it's always the same distance away from that proton. Right? Every single part of that circle is the same distance away from that charge in the center. So it has the same R value all the time. So if I was to go and check out the voltages that would show up when I was on this circle, I would get the exact same voltage all along here, anywhere along that ring. Okay, so that's a really important issue. Same voltage here. So this ring, this circle, because it's always the same radius away, it's always the same voltage. It's a constant voltage line, right? It's an equal voltage line, or what we call an equipotential line. And maybe if you run the numbers, maybe this is like the 10 volt equipotential line. Now, if you go to a smaller radius, maybe you go to a radius that's half as big. Okay, so I'm going to draw a circle in here that's half the size of that, or roughly speaking, half. And if I did that, then if that radius is half as big, then everywhere on that circle would be a 20 volt equal voltage line. And I could play the game again. I could go in to like half that radius. Everywhere on this circle, okay, if it's half as big, is going to have twice the voltage, just looking at this divide by R. So this could be the 40 volt line. And these are lines of equal voltage, so we call them equipotential lines. You would have the exact same story happening over here for the electron, except the voltage numbers would all be a little bit different. So I'm gonna cheat here. I'm just gonna copy all this at once. So, I mean, this will work. Yeah, it's close. So these voltages, because the Q value would be negative, these would all be negative voltages. Maybe this is a negative 10 volt line, and this could be a negative 20 volt line, and this might be a negative 40 volt equipotential line. So these are commonly drawn things. We just never ever drew them in Physics 12, right? These equal voltage equipotential lines, as we call them. Now, one thing I can tell you, just the way the math works, they're always perpendicular to the electric field lines, and that is worthy of a note. So equipotential lines, okay, these equal voltage lines, they are perpendicular to E field lines. Always, without exception. So if somebody gave you, hey, maybe I did, maybe I gave you this picture, which we've seen before, for the electric fields that are happening between multiple charges, right? So these are some E field lines, warnings about force, that's what the blue lines are. And if somebody said, oh, you need to draw the equal voltage lines, where are the places where all of the voltages are equal? All you have to do is draw lines that are perpendicular to the blue ones. You could draw one line in right here. There'd be one voltage at that spot. In fact, if you run the numbers, that would actually be the 0 volt line. And then all I'm doing is I'm just going to do my best to try to draw lines that are perpendicular to the blue ones. Maybe this is a negative 10 volt line. Maybe this is a negative 20 volt line. And I could do the same thing over here. I just go through making sure that as I cross those blue lines, I'm going to cross them perpendicular. Try to cut straight across them. Maybe this is a 10 volt equipotential line, and this might be a 20 volt equipotential line. And it would look like that. Here, well, I don't know, it's going to look kind of like a peanut, right? It's going to kind of go like that. Maybe like this. Maybe this is a 10 volt line, and maybe this is a 20 volt line. It's just an issue of doing your best to draw lines that are perpendicular to the electric field. So we've drawn the electric field a lot, right? Those warnings about force. And now if you want to just indicate where the voltage lines would be, just draw perpendicular lines. It works even better for parallel plates. Let's say this is an 8 volt battery. So everywhere up on this plate right up here, this is like an 8 volt location, and this is a 0 volt location. And then the electric fields, yeah, they're drawn here in blue. Great. They're the warnings about force. No problem. Now, what would the equal voltage lines look like? Well, all I have to do is draw some lines in that are perpendicular to the blue ones. So there's one. Turns out this would actually be halfway. It'd be a 4-volt line. And the 6-volt line, well, you know what? In here, pretty much like that, just perpendicular to the blue ones. But because of the edge effects, yeah, it would have a little bit of a flare up there like that. That would be 6 volts. And then the 2-volt line. The key thing, like the takeaway for this, voltage lines are perpendicular to electric field lines. So these warnings about energy, they're going to be perpendicular to the warnings about force. Now, last page, just going to look at a couple. Oops, that was really bad. Totally disappeared on me. There we go. Last page, we're going to take a look at what happens when you take a conductor, like a piece of copper, and you put some charge on it. Maybe you add some electrons or take some electrons away to make it positive. This is going to be a story about a copper ball, copper sphere, that's actually hollow in the middle. And this is just a knowledge thing. This is nothing but just some raw content. It turns out any charge that you put on it resides on the outer surface. Okay, it's always going to reside out there. So if I was to make this copper sphere positive by actually taking some electrons away, what I would notice is that it would redistribute its charge. The electrons would kind of move around until the surface picked up this positive charge. The surface copper atoms would actually be missing some electrons if I charged this thing positively. You'll find that the electric field in the very center is 0. There would be no force, no field in there at all. And then you wouldn't get any field inside the conductor. Okay, so there's no field in the conductor itself, not inside that copper little ring in there. It's actually a ball. But then there would be field once you leave, and then it would leave perpendicular to that surface of the ball. So these are what the E field lines would look like. So I'm just going to draw these in, and then we'll talk a little bit more about what's important here. I'm trying to draw these arrows, these electric field arrows, coming out of this charged metal ball with a hole in the center. I'm trying to draw them perpendicular to the surface. There's no electric field inside the ball, and the positive charge, the absence of electrons that are migratory, they're not showing up anywhere except the surface. And if you're wondering, well, why can't the electric field like leave diagonally like this? If it did, in addition to having an outward component, it would have an along the surface component. And so here's the little thing that we think of as physicists, is to realize, no, it can't actually be anything but perpendicular. We would say, oh, well, if that electric field, if that E field ran parallel to the surface, well, that would push electrons along. So if that happened, then currents would flow. And if there were any such currents, eventually, since there's no battery in the story, it's just a sphere sitting out in the middle of nowhere, resistance would cause those currents to die away. And so in any kind of steady state, those currents wouldn't be there, and that means that there can't be fields running parallel to the surface. They have to be perpendicular. So no field on the inside, no charge inside the actual copper thickness, but then charge on the edge, causing an electric field that always goes perpendicular to the surface. Next issue, why is it that a neutral conductor, like a little copper ball, would actually get attracted to a charged object? You might think, well, if the conductor is neutral, why does that happen? So imagine this little rectangle with negatives on it is some sort of charged object. It's got some electrons on it that have been deposited there. And in an overly simplified way, I'm going to draw what's happening with a little copper ball over here. So I'm just going to draw like 5 positives. And it's going to be neutral, so each one of these positives, there'd be just the right number of negatives with them as well. Now the negatives are a little bit mobile, right? They can move around, at least the outer conduction ones can. So when I bring this ball of copper near this negatively charged object, some of the electrons on that ball of copper, which are able to move around in that conduction band, they're going to move away. they're going to say, oh no, we don't really want to be close to that negative object. And so now if you look at it, we've separated the charge a little bit inside that copper ball. And so if you kind of imagine splitting this up just mathematically in your mind, you've actually got a positive end of the copper that's a little bit closer than the negative end of the copper. It's kind of gone dipolish on you. And yes, overall it's still neutral, but the positives are closer to this negative object over here than the negatives are. So you actually end up with more attraction than you have repulsion. So you'd have an attraction with this side, and Newton's third law would say the reverse as well, right, on that negative object. And then you'd have a little bit of repulsion over here. And the attraction beats the repulsion just based on distance. So that's why overall this thing would get attracted. Last little item, just something from our Physics AP formula sheet. There's a little change in the way constants are written. So we're very, very accustomed to seeing things written this way from Physics 12. And you'll notice on the Physics AP formula sheet, sometimes they write this equation like this. They take that value of k and they rewrite it as 1 over 4 pi times something called epsilon naught. And then the rest of the formula is still identical. So there's this times q1, q2, all over the distance between the charges squared. And this part right here, this is just a number, and it's exactly the same thing as this value that we've used for k. So we've just kind of bundled all of that stuff together, but it's the exact same thing in the end. It turns out there's a good reason for writing it that orange way. When you're looking at just waves of light, you can calculate velocities a little bit better using that, but this really is the same thing. So don't be bothered when you see that equation on the formula sheet. Both the k and both that orange stuff end up being 9.0 times 10 to the 9. Okay, at least do a couple sig figs. And that marks the end of this day for the extra little topics for Physics AP. And next day, actually the next 3 days, we'll take a look at capacitors.